Excellent. Thank you so much. And I really appreciate the opportunity to speak in this fantastic symposium. So I'm the last speaker between you and you travel back home, so I try to entertain you. And today I'd like to talk about our efforts to learn quantum chemistry with neural network. And it's a privilege to be the last one, and because I can easily skip all the methods since you all know about that. So I'd like to start with the philosophical question. So what would be the ultimate dream of the computational chemist or physicist? Anyone can guess? Good one? More? No? That's a good one too. Well, when I think about being a computational chemist myself, I think about that you come to a computer, drink coffee and do some, design on the machine, and you come up with this amazing molecule. And then magic happens. So the angel come, and experiment work, and your experimental colleagues could synthesize your molecular material, and everything's fine, the microstructure is perfect, and eventually you can go from molecule to final products. And here, in this cartoonish presentation, you can think about all the challenges of system complexity, lengths of times and scales, and accuracy of the models. And one of the problems we've been working is to how we can use machine learning to accelerate quantum mechanics. So if you look for the, for example, ground state, Schrödinger equations, you can think about it, and from the machine learning of a point of view, and you can scoop all the complexity in this function f. You put your molecular feature to predict energy. For that reason, we use neural network, and again, all discussed during this week about all the good things with neural network. Now, in my lab, we use machine learning, and I tend to kind of see on this tool as a multifaceted tool, as the Swiss Army knives. So over the past few years, we applied machine learning for various domains with material science as part of the Aalto initiative. So we developed a set of tools to predict properties of materials. We extended this very recently to two-dimensional materials. We use machine learning to guide experimental colleagues and design of molecules. Again, tools to visualize chemical space, drug discovery, and some of the generative models. But today I'd like to talk about our work, how we can design a transferable of essentially empirical force field with neural networks. Now, if you're interested in applications of machine learning in chemical sciences, so last year, together with my colleague Aaron Walsh, we put up this perspective in Nature when we look on the kind of tiers of applications and use of statistical methods in chemistry in Nature. So if you're curious, please have a look on it. Now, again, so in my lab, we work on the development of transferable neural network potential. So currently, we have a potential for 7 elements. So our claim is if you draw me a molecule with the 7 element, will give you energy and forces. We also work on extending, so we have a 9-element prototype with phosphorus and more elements. Our baseline method is this particular functional, omega B97X, from Martin Head-Gordon. It's one of the latest and more accurate functional. So we call our neural network ANI, and to my knowledge, this is one of the first examples of transferable neural network when you can train on smaller molecules and learn larger systems. And so why we call it ANI? So this is ANI. And given proper training, what I would like to achieve is that my Padawan neural network became DFT Jedi Master. And hopefully, we would avoid this doomsday scenario, so none of us would be killed in these destinations. And you see how hard we work on this acronym to satisfy our Star Wars nerdness, but also not to be sued by LucasArts for the copyright. Now, if you look for the, kind of this cartoonish representation, when you have a kind of a metric of accuracy versus the scale of the methods, and you can build the ladder of those methods. So if you're looking for application for mesoscale system or proteins, basically, you have to rely on a simple, maybe linear scale methods or a force fields. However, as you climb up to the ladder, basically you see, the complexity increase. And if you're kind of looking for, state-of-the-art methods like couple cluster, basically you stuck for only a few small molecular systems. So over the years, we actually developed a couple of different force fields that try to push this to this left corner. Now, it's all good, but there's the ugly part of that. So this transferability actually requires tons of data. And so the first generation of ANI actually been trained to 20 million data points of QM calculation, small fragment-like molecules from 1 to 8 heavy atoms, sampled from real and GDB databases. So those methods are extremely data hungry. And then basically you do proper statistical practice, you split your data, you train, validate, and then you can test it in 2 regimes. And what is typically done in the computer science field, basically you allocate portion of your data, and you test on the data that comes essentially from the same distributions. So if you use small molecules to up to 8 heavy atoms, you test on the same molecule sizes, which we called interpolation regime. However, as a chemist, I would argue that try to push the boundaries and look how good it will work on larger systems. It's more of pragmatic interest to us as a chemist, because you will use those methods for new molecules to do some kind of discovery. And the way how it's done, basically, if you look for distribution of the molecular sizes on this graph, so this blue would be the size of our training data. And over the years, basically, we developed a bunch of this extensibility sets that probes up to 100 and more heavy atoms. So just give you an idea, again, we in the realm of the organic kind of drug-like molecules. So in this benchmark data sets, you have your typical kind of drug-like molecules, greasy molecules, and also we just for fun, we put a couple of smallest proteins. You can actually run DFT of them. So there's 300 atoms in the systems. Now, I think what's important and what's been emphasized in the previous talks, if you still do random selection of your data, you should stop and don't do this, because those you can really use and take advantage of the active learning. First of all, to understand where your methods might not work, where you have poor data coverage, where overfit. And so we've been using, for example, an ensemble of disagreement as the simplest way of the active learning. You can think about in simple term, you have certain phase space and the prediction quantity. So if you train an ensemble of neural network, you make a prediction, what you can see is that actually there's certain regions of the space where the predictions agree, and where they disagree. Now we can go to our oracle and run a quantum mechanical calculations, and basically what you realize that if you have a good data coverage, basically the predictions would agree. If they disagree, basically typically have a bad data coverage. So in this paper last year, we come up with a set of criteria and thresholds how to use and guide these data selections. And the beauty of these methods, basically, this disagreement, but you don't have to run the KM calculation to understand if the quality of prediction good or bad. Now, what it allows you to do is actually active learning framework, fully automated parameterization of those methods, where essentially you throw a kitchen sink of your data sources, presented to an ensemble of methods, and then whatever is above certain thresholds, you run on a compute cluster, update the database, retrain. And basically this loop is fully automated. It's great for students. You don't have to do anything. to make your work keeping going. Now, when you train those methods, and basically now you can use them as your standard energy function and plug into any type of applications you look in. So what sort of accuracy you can achieve? You can get an accuracy within 1 or 2 kcal per mole for total and relative energies. And I'll give you an example here, a couple of hard to do with classical force field organic molecules, for example, with sulfur, a lot of halogens, and you can see the accuracy of the prediction for a range of different conformations, but also basically a quality of potential energy surface, which is almost indistinguishable from the reference QM energy. So it'll give you high quality energy functions within a 1 or 2 kcal per mole. Just to put this into perspective, how it's comparable to standard semi-empirical methods, for example. So here what I plot you, the relative energies of different conformers. So any neural network here in red. So the perfect fit would be the straight diagonal. So we get the error, about half kcal per mole. And you see, for example, density functional tight binding or semi-empirical method will give you much, much larger errors for the conformer hierarchy. Now, in addition to energies, we can learn properties. So, for example, charges and partial atomic charges. Charges is an interesting example. And because charge is not physically observable, and that's why we have 50 different charge schemes. So we've done in this paper, we ask a question, can we ask neural network to assign the charges? So what we did, basically, because dipole is a physical observable, we ask a neural network to assign the charges to reconstruct QM dipole. So we'll give you a dipole consistent charge scheme. And basically, these plots give you accuracy of prediction of dipole given the reconstructed charges. In addition to dipoles, what was interesting to see that quadruples also are quite nicely represented, despite the fact we didn't constrain them. And this cross-correlation plot here will give you a relationship between different charge schemes, and you can pick your favorite scheme like Hirschfeld, NBO, or MSK, and basically you see the charges all over the place. But what was interesting to see that our neural network assigned charges very nicely correlate with the CM5 charge model 5 scheme from Chris Kramer, which are essentially a dipole consistent charges fitted to experimental dipole. So a neural network may give you actually an unbiased way how to reconstruct and get the charge scheme. Now we have energy, we have charges and dipoles. Now we can do full-featured molecular simulations. So what we've done here, we run a molecular dynamics with neural network using ML potential, calculate charges, reconstruct dipole, all done with machine learning. And we can calculate quite accurate dipole IR spectra. So here I show you prediction with machine learning in red and QM reference in black. And just to do a reality check, we took certain snapshots and look for the accuracy of charges and dipoles, and you can see a very nice correlation between ML predicted and QM dipole. Now, there are for certain applications, the accuracy of density functional may not be enough. So what we've done recently is, how we can use efficient couple cluster calculations, essentially to achieve a state-of-the-art accuracy and simulations. Again, even with the Moore's law and the growth and the power of the machines, so doing, I apologize, should be CCSDT, doing high throughput couple clusters calculation in the complete basis set limit is still not possible. So we think about it, and basically we come up with a trick. So if you look for a standard scheme for extrapolation of the CBS energy. So this couple cluster term, it gives you the computational bottleneck. So we apply extrapolation scheme inside the extrapolation scheme to approximate this term with the DLP-NO approximation of couple cluster in couple different thresholds. But what it allows you to do, essentially maintain the same accuracy, but get you a really much faster speed up in terms of compute. And then we can combine our active learning training scheme and the transfer learning. What we've done, we took our baseline DFT trained neural network, and we run active learning using the couple cluster CBS data, and retrain part of the parameters in neural network. Overall, what we run few cycles of active learning, we calculate probably 500,000 of those couple cluster calculations, and ended up with essentially a Frankenstein method, which is neither DFT nor couple cluster, somewhere in between. But I'll show you a couple of applications that essentially this hybrid Frankenstein method is exceeding accuracy in DFT. And one of the applications where DFT actually might not give you a reliable prediction, for example, reaction energies. So if you look for the strain compounds like that and energies of isomerization, where you see formation or disappearance of the conjugated these bonds. So what this plot shows, so reaction ID versus essentially an error. And if you look for our reference, which is omega B97 in blue, for certain reactions, you get the error in the reaction energy 20 kcal per mole. For this particular one, 40 kcal per mole. It's actually the disaster when you have energy of 40 kcal per mole error in the reaction predictions. And therefore, the neural network being trained on DFT data actually mimics those errors. However, the neural network being retrained with the couple cluster data essentially gets you error within 1 or 2, and none of the system actually here been part of the training data. So this is really true extrapolation. Now we can combine all these tricks. So what been working in past year about rethinking and using more sophisticated architecture. So we come up with this IMNet architecture. In addition to a modular structure, we can train to multiple different things. And in addition to energy, you can predict properties. And for example, here in this paper, we get energy charges, atomic volumes, and also a continuum solvent correction. So what it allows you to do is predict all those quantities in one shot. And one of the way how we probe the accuracy of that, we went to the database of experimental solvation free energies, called MN-Solv, at the University of Minnesota, which have those experimentally measured high-quality solvation free energies. So what we've done now, we can calculate Gibbs free energy in gas phase, use neural network, the solvation energies in the solvent, take a difference, and basically compare it to experiment, and it gets us about 1.8 kcal per mole error. And this accuracy actually within the accuracy between different solvation models or different DFT functionals. And in addition, we look for the quality of prediction of the potential energy in the solvent as well. But also we can look for the atomic representation, what's been learned inside the neural network. For example, we can look for atomic embeddings for different atoms, and they kind of line up nicely as in the periodic table when you have this x-dimensional group and the period, and you see oxygen, sulfur, the halogens. But interestingly, hydrogen we learned more to the halogens, which makes chemical sense. We can zoom into these regions and look for the structure of each element. So, for example, in carbons, you can look, what type of a neighborhood connectivity, and polar, non-polar substituents, and for example, the hydrogen, interestingly, dominated by the essentially the heavy atom it connected and type of the carbon. So you can look a little bit deeper what's neural network been learned. How much time do I have? That's fine. With that, let me wrap up. Excellent. Let me wrap up, and what I'd like to do in last few minutes is maybe to show where I think some of the future directions of the field, maybe a little bit concentrated on our work. So what I think, very soon we will see those from the really experimenting and experimenting with the training of those methods, we will see new applications and of those methods. So what we've done recently, we take our neural network been essentially trained on a small molecules. We have again 7 elements. We add a little bit data on the individual amino acids. So when I go to a PDB and pick a proteins that have 7 elements and has the a ligand sitting in the active site, so it's a particular protein. So what then I've done, I took this protein, put in a box of water. So the total system size of 30,000 atoms. Again, we have explicit water. At this point, we don't have ions yet. So this is your distilled water protein simulation. And we get some heteroatoms in the active sites. So we plug it to Amber. We run a molecular package. We run a molecular dynamics. And I am meeting the water here. And this is a really boring movie. Nothing happened. Didn't explode. I think this is great example that a potential learned something. Protein didn't default. The ligand still sits in the active sites and gets the interactions. And if you look at MSD, basically you get some thermal relaxations and it's stable. We run it for 20 nanoseconds. It looks great. So I think this is the hope that we can really design a transferable force fields for biomolecular simulations soon. And as the bonus of these methods, we can solve the problem of the force field based simulations because our force fields are fully reactive. So one of my students, what he did when he ran the simulation, he ran a default a protein preparation, and he done the most frequent error. He did essentially get the protonation state wrong. If you look for this arginine and the carboxylic acid, actually carboxylic is protonated. This is wrong. So when you run this simulation, actually what you observe is this proton shuffled, and you see the arginine is get protonated and is get protonated. So you can describe a covalent inhibition. You can describe the proton transfer events in the system. So it can help us to do the enzymatic application of enzymatic catalysis better. But I can crank up challenge even more. And again, we add a little bit carbon-carbon bond breaking data, but otherwise it's the same force field. And we've done a crazy thing. So I take 4,000 hot carbon atoms in the hot, it's very high temperature, over 2,000 Kelvin simulation. Again, it's periodic boundary conditions. 4,000 atoms, high temperature. You run it for a few nanoseconds, so you start from random gas, essentially. And then what you see, the magic happens. You see the nucleation of the graphene flakes. You see the formation. There's a buckyball here. And then some of these flakes and buckyball grows. You see small nanotubes, things like that. So probably the the quantitative agreement of this simulation is wrong. But qualitatively, what the potential learn is the carbon wants to be conjugated 6-membered rings. And what we see here, so it's my hope that it learns enough chemistry and physics underlying. And also what's interesting, a few years back, late Professor Manakuma done simulation like that. So it took them a year on a large supercomputer machine, and they published it in Science. Now, the same kind of simulation now accessible to you, essentially on a laptop and a GPU, and the simulation takes a few hours to run. So you see acceleration of science for most of us who don't have access to these large machines. And it also gives hopes that those potentials are learning enough to predict new science as well. So with that, let me wrap up. So if you're interested to use that, it's all on GitHub. We have Ani connected to ASC Python environment here. We also have a fast PyTorch implementation. We've done connectors to Amber, OpenMM, and LAMPS in progress, so this will be available soon. So if you're interested in using our data again on GitHub, it's been used in many academic labs, government, and some industrial partners as well. And finally, let me acknowledge, this work will not be possible with essentially work by graduate students in my lab, in Adrian Roiber's lab, University of Florida, collaboration with Los Alamos, our funding agencies, and of course, a lot of computer resources to run our reference quantum. And with that, let me finish and leave this links for you. Thank you.
Thank you very much for this impressive talk. There's a question over there.
Thanks, impressive work, and congratulations on this. So I was interested in your last protein simulation. Since you see these exchanges of protons when you have the wrong protonation state, do you see enough events, for instance, to see if some of the titratable groups where there are experimental pKa values established, that you could actually compare them and see whether you get also compared to this sort of more soft experiments?
That's our plan. We didn't do it yet. So the drawback of that, since this is a fully reactive potential essentially, your time step is the 0.1, 0.2 femtosecond. So it's hard to achieve a macrosecond simulation. So essentially those simulations 10 times more expensive because they're reactive. So it's harder to do the time scale, but that's on our list to check the titratable groups for sure.
More questions?
That's absolutely amazing. That's great work. Where do the non-covalent interaction come from in the training data? Because as far as you've seen molecules with up to 8 atoms, so there's non-covalent interactions.
In original data set, yes, it was only 8. Now we train a little bit larger system, but again, we cheat a little bit. Basically, I use D3.
Okay.
And you don't have to learn it. You just add it because it's analytical. And
you're running it to the neural network or to the omega B97XD?
So we subtract D term. You train essentially on the DFT part.
Okay.
And I add dispersion ad hoc, the same way how it's done in DFT.
Okay. That makes perfect sense. Yeah.
More questions? Is this a question or final remark?
So how fast are these potential compared to what else is in Amber? And I'm asking this because there was an amorphous carbon workshop here in Helsinki, and they had compared the gap potentials that are in Amber, and although they were very accurate, they were too slow for what the community needed for these mega 100,000 atom simulations. So in your case, how fast are the neural network potentials once they're in Ember?
Do you know how fast is that potential? Is it millisecond?
Oh, I don't know the numbers.
So our CUDA code, which is the first link, is slightly slower than classical Amber type potential. It's much faster than probably GAP and ReaxFF.
Okay.
More questions? The other one?
First of all, on this last question, why is it so much faster? Because it's implemented on GPU, while ReaxFF is just simple CPU. I mean, it has a lot of more parameters, right? So it's 1 million parameter at a point, while ReaxFF is probably hundreds.
Yeah, the way basically all those tensor operations very act, and essentially it's a bunch of BLAS calls fused into one.
Okay, makes sense. Actually,
And you don't do, because in ReaxFF you add, you calculate all these different terms, then sum together. So probably it's done less than optimal. But neural networks been streamlined with the work of a lot of engineers in the top companies. So
makes sense. And the other question is on learning charges that you did at a point, and of course you then use it to model long range, I can imagine, right? So basically you model the charges only implicitly and fitting on dipoles, right? That's your approach. But I can really see that there is some intrinsic ambiguity in how you assign charges in order to obtain a single fitting data point that is a dipole, right? So there is some degree of freedom that you are really free to explore some space of possible assignments, and then you choose one. I mean, the neural network chooses one only.
I was very surprised. So absolutely agree. You can reconstruct a dipole with arbitrary charges, but it kind of leaned to a CM5 scheme, which just kind of makes sense. That was surprise. I have no rational explanation why it happens.
Okay, that's what I was going to ask.
Magic of deep learning.
Okay.
Any other questions? Otherwise, I think we should thank the speaker again.